This is session A3, Max Planck and Blackbody Radiation, 1901. Last session we talked about 5 scientific discoveries from the 1800s, and now we're continuing with 1901. Blackbody radiation, I will explain what it is later, but it was an aspect of physics for which there was a classical theory and formula that disagreed badly with experimental results. Planck worked for a couple years and finally was able to produce a correct formula for the effect and a physical explanation for the formula. He did that in this 1901 paper on the distribution of energy between ether and matter. Written originally in German, Max Planck was a 43-year-old German physicist. So mature, professional, not young. He wrote his paper in German. I wasn't able to find an English translation in Google search, and the original paper is not available for free. So normally I would like to read the paper before producing these videos, but in this case I worked from a book I have and a number of Wikipedia pages, which you can look at if you want to know more. The upshot of Max Planck's discovery will be that light energy is quantized in one special case, this blackbody radiation, which we will talk about. So quantized meaning it can only exist in certain definite energies, not in arbitrary amounts. This is not consistent with classical physics, and this will force the beginnings of quantum mechanics. Max Planck was not trying to contradict classical physics. He didn't want to contradict classical physics. He reluctantly came to the conclusion that light energy is quantized in order to produce the correct formula that agreed with experimental results. He was desperate to solve that problem, but he wasn't a revolutionary, and he wasn't a young, bold physicist like Einstein at age 25 would be. Now, in this video, I could just tell you the final result, but I don't want to do that. I'm afraid that if I just tell you the final result and it's a short video, that your takeaway will be, yeah, okay, sure, that's pretty obvious. What's the next video? But although Planck was not a revolutionary, his result is revolutionary, and physicists' reaction were not, okay, sure, that's obvious. Physicists' reaction were, what the heck is this? This is not classical. So this video is going to be longer than you might like, and it's going to go through a middle level of detail about how did Planck come to these conclusions and how do they relate to the experimental results. I want to give you enough background that his final physical hypothesis of energy being quantized will have some background for you. But it means that I'm giving you a lot of equations. You don't have to follow all the equations. You don't have to understand them all. Some you will understand, some you might not. That's okay. If you don't follow all the equations, or you don't like all the equations, you can ignore most of them. But pay attention to the few that are in green highlight. Those are most important. Those are important to future lectures on quantum mechanics and important to quantum mechanics. I'm giving a lot of graphs here, and if you either can't follow the equations or don't want to follow the equations, I hope that you can at least follow most of the graphs. And if you do follow the equations, the graphs will help you anyway. However, if the number of graphs is too much, don't quit the video. try to watch to the end, follow the general story, not the details. Pay attention to the green highlighted material. And if with everything I've said you don't like this video, don't give up on the lecture series. They're not all this way. Try the next video. This is unusual in the amount of equations and graphs I'm giving. Okay. This is a possible time to take a break. We're interested in a phenomena called blackbody radiation or thermal radiation. When a body is at some temperature, it radiates light. It may be visible light. It certainly will be infrared light, which we feel as heat. We don't see it, but we feel it. For an ideal body, the amount of energy that gets radiated is linearly proportional to the absolute temperature to the fourth power. So the temperature in this paper will always be in Kelvin, which is an absolute scale. Won't be Fahrenheit, won't be Celsius. So if the temperature increases by a factor of 10 in Kelvin, the amount of radiated energy, infrared and visible light total, if the temperature goes up by a factor of 10, the energy radiated will go up by a factor of 10,000. Sigma is a constant that it gets the name Stefan-Boltzmann Constant, and it has this value in watts per square meter per Kelvin to the fourth. So when you multiply times temperature to the fourth, the radiance that you get out is watts per square meter of the emitting surface. Radiance is also known as radiant emittance or radiancy. As far as I can tell, those mean the same thing. So thermal radiation is self-luminous emission as a result of the body's temperature. It's not reflection of ambient light. All bodies emit thermal radiation to their surroundings, and they absorb thermal radiation from their surroundings. If a body is hotter than its surroundings, it emits more thermal radiation than it absorbs, so it will tend to cool. Its temperature will fall, and its thermal radiation will fall. If thermal equilibrium is achieved, the rates of emission and absorption are equal. Let's look at a case of our human bodies. If it's cooler outside than your body temperature, you will radiate more energy than you absorb from the environment. Your body would cool off, but we're constantly putting more energy into our body in the way of food and metabolizing that food. And it's important for mammals that our body temperature not fall very much. So our bodies thermally regulate and try to keep a constant temperature. But a body like a stone or a ball or something that has no internal heat source will behave, as I said, in terms of emitting radiation and temperature falling. Now, if it's hotter outside than our body temperature, we'll absorb more thermal energy than we radiate, and our body temperature would go up. So in addition to radiation, our body has other ways of regulating its temperature. We sweat, and there's other mechanisms for getting rid of excess energy and maintaining a constant temperature. Now, Stefan's law comes from 1879, but the Stefan-Boltzmann constant came later. It was experimentally measured. There was a theory of what went into the Boltzmann constant, but it wasn't the final theory we're going to see today. Physicists lacked a good theoretical physical formula for the Stefan-Boltzmann constant sigma. This is a possible time to take a break. Let's take the sigma t to the fourth formula and graph it for different temperatures. The horizontal axis here is going to be absolute temperature in Kelvin. If you're not familiar with Kelvin, that's okay. So you may not know how to convert from centigrade or Celsius or Fahrenheit into this scale. Don't worry about that. Just know that it's a temperature scale. The black curve here is the formula sigma t to the fourth, which gives the total radiancy, which will be the vertical axis. And on this scale, that axis is in watts per meter squared, and you could see this horizontal line is 20,000 watts per meter squared. But the curve varies quite a bit from low temperatures to high temperatures. It grows very quickly. So let's start with low temperatures. This green arrow is pointing to the point of liquid nitrogen, 77 Kelvin, and it only radiates 2 watts per square meter of surface area of the liquid nitrogen. This blue arrow is pointing to the point of freezing water, 316 watts per square meter. This brownish yellow line is pointing to our body temperature. We emit 525 watts per square meter radiated power due to our body temperature. That's what we radiate, but we also absorb. So that's not the net total. That's how much we radiate, but not including how much we absorb. I'm not subtracting how much we absorb. This purple-violet line is boiling water, 1100 watts per square meter. This red arrow is pointing to if you were to heat a piece of steel until it looked dull red to you, that temperature would be about 700 Celsius, a little less than 1000 Kelvin, and that would radiate almost 51,000 watts per square meter. Higher temperatures, this graph grows even more sharply, and you get much higher values of radiancy. This is a possible time to take a break. Thermal radiation is also called blackbody radiation. And why is that? We use the word black to mean a surface that absorbs all visible light equally. The color white is when it emits all light equally as seen by human eyes, in the sense that it sort of reflects or re-radiates. So if we shine white light on a white surface, it looks white. If we shine red light on a white surface, it looks red. If we shine blue light on a white surface, it looks blue. But if we shine white or red or blue on a black surface, it looks black. So black is the lack of light, especially visible light. Why are we talking about black bodies, not white bodies? If we had an object that was at room temperature and we viewed it in sunlight, the object is much colder than the temperature of the sun where the sun emits lights. So the object should absorb much more light than it emits. So if it was a perfect absorber, the object should look black in sunlight if it was a black body. Whereas a white piece of paper is not emitting thermally. A white piece of paper looks white even though its temperature is very low. So a white piece of paper is not emitting thermally, whereas a black body is absorbing and emitting thermally. So a perfect absorber is called a black body. Now, real materials are not perfect absorbers. Real metals are not perfect absorbers, but they can be close, and they can be coated with a black coating that makes them even closer, and we can get a good experimental results. Now, there are modern super black materials and coatings, and I'm giving you a link here to a site on YouTube that talks about a material called Vantablack, which is one of the most black materials ever made. It has special uses. You're not going to buy it as paint for your house, but it has very special uses. And if you look at that video tube, you'll be impressed that is a black that you've never seen before. All the objects that you've seen as black in your life, you can see them. They don't look like a hole in space. You can see where the object is. You're not confused about how to touch the object. You know your distance to the object by looking at it. But these super black materials, they're like a visual hole in space. You cannot tell how far you are away from it. Whatever shape it has, you cannot see its shape because it's just total blackness. Now, that's not important to the rest of this video, but you might find that interesting. This is a possible time to take a break. Now, if we take the amount of radiated light, we can examine that as a function of either wavelength or frequency. And when we look at it that way, we are looking at its spectral radiance. As a function of wavelength, the spectral radiance is called B sub lambda, lambda for wavelength, and it's a function of the wavelength and the temperature. It's the emitted radiated power per unit solid angle, don't worry about that, per unit area of the emitting surface, normal to the radiation propagation, of radiation wavelength lambda per unit wavelength at thermal equilibrium at absolute temperature T. Now that's an awful lot of words. But hopefully you have the impression that it's the amount of radiated power per unit wavelength at a temperature. And so it can tell us something about how objects radiate light, radiation, at a temperature. The spectral radiance B lambda has units of watts per steradian, that's solid angle, per meter squared, and we'll use per nanometer, where W is watts, joules per second, power. Steradian is unit of solid angle, 4 pi for a whole sphere, 2 pi for a sphere. Don't worry about it if that doesn't make sense. M is meters squared, and NM is nanometers, 10 to the minus 9th meters, billionths of a meter. Now we can also look at spectral radiance as a function of frequency. Sometimes I will use F for frequency, but in this case, physicists use the Greek letter nu for frequency. And if you were to look at Wikipedia, that's what you would say. That's what you would see. So this formula is called B sub nu, and it's a function of frequency and temperature. So it has slightly different units. you can easily convert from B nu and B lambda with this formula and substituting this, but you're not going to have to, so don't worry about it. But they are, if you knew one, you would know the other. That's the important takeaway. Now, if we had a physical formula for B lambda, that's all we would have to do is integrate it over all spatial angles, and over all wavelengths, and we would get the Stefan-Boltzmann constant. So sigma t to the fourth would be pi times this integral if we had B lambda. So if we had a good formula for B lambda, we could check it by seeing if it produces the experimental result of the Stefan-Boltzmann constant. This is a possible time to take a break. Now, there was a classical model called the Rayleigh-Jeans model. Rayleigh and Jeans were British scientists. I believe they both published independently, but we now just call it Rayleigh-Jeans, but I think they published independently. They had a classical model predicting the spectral radiance. In B lambda form, it was this equation: 2 times the speed of light times Boltzmann's constant times the temperature over the wavelength to the fourth. This is the Rayleigh-Jeans model for the spectral radiance B lambda, but it is incorrect. This formula disagreed disastrously with the experimental results for short wavelengths. And let's look at a graph to see that. This graph is for one temperature, 1000 Kelvin, which is close to dull red. If you took a piece of iron and you heated it, and then it looked in a dark room, it looked dull red to you, that would be 1000 Kelvin. So the horizontal axis here is wavelength in nanometers. Here's the visible light range from red to violet. The vertical axis is spectral radiance in the units that we gave before. The black curve is the Rayleigh-Jeans model. The orangish curve is the actual model if you were to experimentally measure it for 1000 Kelvin. So the Rayleigh-Jeans model is a good match for very long wavelengths to the right of this graph and far to the right. But as we move down in wavelength, it gets more and more hopelessly wrong, because the Rayleigh-Jeans model continues to increase as we go to smaller wavelengths, whereas the actual model has a peak and then it goes back down to zero. So this Rayleigh-Jeans model is horrible at small wavelengths. In this case, visible light. At 1000 Kelvin, there's very little visible light. There is enough that we do call it red, but almost all the energy is in this infrared band, where it's radiating and we feel it as heat. If you were standing a foot away from 1000 Kelvin heated piece of iron, you would feel the heat radiation coming off of it. So almost all the energy is in the infrared. This Rayleigh-Jeans model says, no, you should have tons of visible light and tons of infrared light. And it's just wrong. That's not how nature behaves. If we look at ultraviolet, which is just on this graph, it's to the left of this violet line, left of visible light. The Rayleigh-Jeans model would predict that there would be a ton of ultraviolet, and there is none. Physicists in 1900 and 1901 knew that this was a real big problem. It later got the name ultraviolet catastrophe, but that name came 10 years after Planck had solved the problem. So we still call it the ultraviolet catastrophe. And it's a useful name to express how bad the Rayleigh-Jeans model was, but it actually wasn't the name that physicists were using in 1901. Now, we can look at a Rayleigh-Jeans model expressed in terms of frequency, and we would get that it should be proportional to the square of the frequency and proportional to the temperature. And we can graph that for the same temperature, 1000 Kelvin. Now the graph looks different because here the horizontal axis is frequency. So left is low frequency, long wavelength, and the Rayleigh-Jeans model predicts that the spectral radiance will just keep growing as we go to higher and higher frequencies. But the actual result is that there's a peak at some frequency. In this case, it's still in the infrared. And then the radiance goes down, and it's very little in the visible light and nothing in the ultraviolet. Here's the visible spectrum, red to violet, and it's almost all infrared. So this has the same information as the wavelength curve, but the graph is different and the horizontal axis is different. We could use either one. You will see either or both graphs if you look at Wikipedia pages. This is a possible time to take a break. So now we want to understand how the classical model went wrong and how Planck got the correct model and what the correct model means, because it actually means that we're going to need quantum mechanics. Planck doesn't know that at the time. Other physicists don't know that at the time, but we know that now. And so that's why it's worth understanding this a little bit. If I just give you the answer, I feel that you won't appreciate how revolutionary it was, and therefore how revolutionary quantum mechanics had to be. So this will be kind of a long lecture with a lot of equations which you don't need to know and a lot of graphs which hopefully will make some sense to you. Now the actual experiment that Planck wanted to match he wanted to produce a formula to match the experimental results for measuring the spectral radiance in what's called a black body cavity. And here's an idealization of that setup. We have a hollow, rigid, opaque, electrically conductive rectangular box, three-dimensional rectangular box, externally heated uniformly to a constant temperature T. We'll have different experimental runs at different temperatures. At each temperature, we will get an experimental curve of the spectral radiance. Inside the cavity, in thermal equilibrium, there will be electromagnetic radiation, visible light and infrared light, in thermal equilibrium with the cavity walls at temperature T. That'll be true whether there was vacuum in the cavity or air in the cavity. Now we're going to have one peephole in the cavity, and we're going to look at the light that comes out. We're going to shield it so that light emitted by the outer walls we don't view. So we're only viewing the light that comes through the peephole. That'll be thermal cavity radiation. It'll be mostly infrared light, but also visible light coming from the inside of the cavity through the peephole. We could measure the total power that we see, but what we want to do is look at that cavity radiation as a function of either wavelength or frequency, because the shape of that curve is going to change for different temperatures, and that'll give us information about what's happening inside the cavity and in the walls of the cavity. This is called a black box. Why is it called a black box? The walls of the box don't have to be coated black. They could be coated black. They have to be electrically conductive. They have to reflect some amount of light inside the box. The reason why it's called a black box is if some light were to come into the box through the peephole from right to left, it would go all the way through. It would reflect off this wall. Maybe it would reflect and hit here, and then it would reflect here. It would bounce around the box. But every time it hit the walls, some of it would be absorbed and some would be reflected, and none of that energy would end up coming back out of the box. And so if the temperature of the box was low, like room temperature, and we looked inside the box, it would look black in invisible light, which is why we call it a black box. And in fact, we can make a better black box cavity than if we just take an object and just heat it and look at its radiation. Because the object has a color, and it has various materials properties, and even if we coat it pretty well, it turns out this cavity is a good model for black body radiation. This is a possible time to take a break. The peephole in the cavity has the same electromagnetic radiation as an ideal black body's emissions, depending only on the temperature and not on the specific materials of the walls of the cavity. So in this case, cavity radiation is the same as thermal radiation and the same as black body radiation in this case. Now, the speed of light in vacuum is independent of the wavelength, and that's pretty true in air too. So we could derive the spectral radiance formula if we knew how much energy density was present in the electromagnetic waves inside the cavity. If we knew the electromagnetic wave's spectral energy density, how the energy in the cavity varies as a function of either wavelength or frequency, we could calculate the spectral radiance. So if we had the spectral density rho, in this case rho of wavelength lambda, if we knew that function, the spectral energy density, we would just multiply by this constant and we would get the spectral radiance. So the way that physicists analyzed the black body cavity is to develop a theory for the spectral energy density rho of lambda. So they developed a theory for rho, and then experimentally they could verify either B lambda or B nu for frequency. This is a possible time to take a break. The metal walls of the box are electrically conductive. This means that the electric field will be zero or very small at the walls of the inner walls of the box, which means that there will be a node of the electromagnetic sine wave there. If you're not familiar with the electric field, don't worry about it. I'll show you the sine waves and explain more. So the electric and magnetic fields inside the box, they'll be electromagnetic standing waves, and I'll explain what that means, with definite discrete wavelengths and frequencies determined by the length of the cavity. Because they have to have nodes, zero amplitude, at all the metallic walls. So you can only have certain wavelengths and frequencies that fit in the cavity such that the electric field at the walls will always be zero. Now, what is a standing wave? In one dimension, here's a standing wave. I'm only showing here the z direction, so the electric field will be a function of the z direction and a function of time. It will be some quantity that does not vary with distance or time times a sine wave of a function of distance times a cosine that's a function of time. So the spatial part is separated from the time part in a standing wave. So it's not traveling in the z direction with time. The z component is given as a spatial function of a distance, and it's not traveling in time. Now, mathematically, the standing wave can be looked at as a sum of an incident light wave and a reflected light wave, two identical traveling waves traveling in the opposite direction. So it can be thought of as the light is going to the left, and then it reflects off the left boundary and goes to the right, and reflects off the right boundary and goes to the left, and it keeps bouncing back and forth. And mathematically, we can turn that into this equation. And here is a GIF image of a standing wave from Wikipedia. The black sine wave is the standing wave, and the red and blue waves are traveling waves. The red is a traveling wave to the left, the blue is a traveling wave to the right, and when you sum them, they produce the black standing wave. Now, in order to match the cavity, there are some constraints on this equation. We can only have an integer number of half wavelengths of the radiation equaling the cavity length. That condition gives us the nodes at the cavity walls because the cavity walls are electrically conducting. So if the length in the z direction is Lz, we can only have wavelengths, lambda sub n, whose half wavelength, lambda sub n over 2, times integers 1, 2, 3, and so forth, matches the length. So we can only have wavelengths that are twice the cavity length divided by integer n for any integer n 1, 2, 3, so up to infinity. So we can have a lot of different wavelengths in the cavity. But they are definite wavelengths. They are not arbitrary continuous wavelengths. They're definite given the length of the cavity. Now, for every wavelength, for every value of n, we get a wavelength from this formula. We get a wave number k sub n from this formula, and that k sub n is what goes into the sine formula, sine k sub n of z. We get an angular frequency omega sub n, and that goes into the cosine omega sub n t part of the standing wave. But the amount of electric field can also depend on the integer n, and that's what this E of n term is. Now, frequency f or nu does not show in this formula, but there's also a formula for frequency. This is a possible time to take a break. The electromagnetic wave wavelength, frequency, and wave number, k, they're quantized in the cavity. These are cavity modes. They're quantized because the cavity has a length and the cavity walls are electrically conductive, meaning that a sine wave has to have a node at the wall. Here I'm going to show just some examples of sine waves that are valid cavity modes in one dimension. So the cavity goes from here on the left to here on the right. That's where the walls of the cavity are. For n equals 1, we have this red curve, which is 1/2 a wavelength. It has a node at the left and a node at the right, and the half wavelength fits in perfectly fine in that length. So that's the longest wavelength, shortest frequency mode, cavity mode, for this cavity. For n equals 2, we have 2 half wavelengths. The sine wave goes up, and then it goes down, and then it comes back to 0. And we can have 3, up, back to 0. We can have any integer number higher, 1 or higher. We can have 30 and 31, 60, 240. And in principle, there's no upper limit. Physically, there might be an upper limit, but mathematically, there's no upper limit. So we can have very short wavelengths, very high frequencies in the cavity. This is a possible time to take a break. So we found that the cavity mode frequency had this formula: integer n times the speed of light over twice the cavity length in one dimension. This frequency is proportional to n. So that made it easier to develop the theory for the spectral energy density in the frequency form. Rho sub nu was easier to produce the formula for, and then that could be converted to the energy density in wavelength form, and then it could be turned into the spectral radiance formulas and then measured experimentally. So Rayleigh-Jeans they produced the spectral energy density rho sub nu. And the units for rho sub nu are energy joules per unit volume, meter cubed, per unit of frequency, so per hertz. Rayleigh-Jeans determined that the number of discrete cavity modes in 3 dimensions, so not our 1 dimensions, and correctly counting the allowed polarization directions, which we didn't talk about, the number of cavity modes in 3 dimensions in the frequency range, the small frequency range, which we call differential frequency range, from frequency nu to frequency nu plus a little bit of frequency, d nu, is this amount. The number of cavity modes times the differential in frequency is 8 pi times the volume, v, over the speed of light cubed, times the frequency squared times the differential in frequency. This is a possible time to take a break. So Rayleigh-Jeans, now that they had the number of cavity modes, they needed to also determine the average total energy for each cavity mode. They applied 2 results from classical kinetic theory, also called statistical mechanics. Statistical mechanics assumes that matter consists of atoms, that classical physics applies for those atoms, but that large collections of atoms are governed by probabilities. Now in 1900 and 1901, physicists expected that matter probably was consisted of atoms, and they had some ideas about atoms, and their theories did rely on those ideas about atoms, but it wasn't considered proven that matter consisted of atoms. So the theory could be right or the theory could be wrong, but Rayleigh-Jeans produced the theory and then looked at the experimental results. So Rayleigh-Jeans used 2 results from kinetic theory. The first result is called the Boltzmann probability distribution for the probabilities of energies in thermal equilibrium at temperature T. So the probability that a state will have energy E is this formula, 1 over kT times the exponential of minus E over kT, where K, which you'll often see written as K sub B for Boltzmann, is Boltzmann's constant with this value, 1.38 times 10 to the minus 23 joules per Kelvin, so energy per temperature unit. So K times T has units of energy. This becomes energy divided by energy, and then this is 1 over energy, probability at an energy. The second result from kinetic theory that they used is called the law or theory of equipartition of energy. It says that all independent modes of a system have the same average energy in thermal equilibrium, and that the amount of that energy will be a constant times kT, Boltzmann's constant times temperature. This constant depends on things we're not going to worry about. Sometimes it's half, sometimes it's 3 halves. It depends on more detail than we're going to go into. Rayleigh-Jeans assigned to each cavity mode, to each standing wave, the average total energy, E with a bar over it, of kT. This produced the Rayleigh-Jeans spectral energy density for blackbody radiation, rho of frequency is this formula: 8 pi frequency squared kT over speed of light cubed. But this formula disagreed disastrously with the experimental results for high frequencies, short wavelengths, as we saw in the graphs. This is a possible time to take a break. In 1900, Planck tried to fix this, and in 1901 he succeeded. He was able to determine the correct spectral energy density function that matched the experimental results pretty well by keeping the Boltzmann probability distribution assumption, but abandoning equipartition of energy for blackbody cavity modes and replacing it with a new understanding, which over time would be understood as a quantum mechanical break from classical physics. Planck wasn't trying to break from classical physics, he was just trying to explain blackbody radiation. But his formula turned out to be correct, and his explanation turned out to be correct, and his explanation would become a break from classical physics, even though that wasn't his intention. Planck found the following conditions gave a formula that matched the experimental results. The Boltzmann probability distribution did apply to cavity modes. 2, the total energy of a cavity mode standing wave of electromagnetic radiation in the blackbody cavity can only take on definite discrete energies, not a continuous range of energies. So the wavelengths and frequencies are quantized because of the cavity length, but also the energies in the cavity modes are also quantized. For a cavity mode of a given electromagnetic frequency, nu, the total energy of that cavity mode can only be some integer multiple of a definite energy amount that depends on the frequency. So take m to be an integer that could be 0, 1, 2, 3. The total energy in the cavity mode is that energy times, that integer m times a definite energy amount, delta E sub nu, that can depend and does depend on the frequency. The total energy of the cavity mode cannot take on arbitrary continuous energy values. This is different than what the equipartition of energy theorem produced for Rayleigh-Jeans. When the energy amount as a function of frequency is much smaller than the energy kT for a given temperature, then the average total energy for that cavity mode will be approximately kT, and Planck's model matches the classical Rayleigh-Jeans model for those frequencies for which this formula is true, an equipartition of energy will be approximately true in that case. However, when the energy increment for some frequency nu is much larger than kT, the average total energy for that cavity mode is going to be much less than kT. This stops the ultraviolet catastrophe if we have large delta E when the frequency is large. This is a possible time to take a break. Planck matched the experimental results when he took this specific linear formula, that the quantum of energy at a particular frequency nu was a constant h times the frequency nu. And then experimentally he found that the value for that constant, which we now call Planck's constant, is 6.63 times 10 to the minus 34 joule seconds. Don't worry about that value in this lecture. That value for Planck's constant h gave a good fit to the experimental results. Planck later called this formula an act of desperation to match the experimental results. He wasn't trying to be a revolutionary. He was just trying to match the experimental results. Nowadays, we would say it this way: the photon energy E is equal to h times frequency nu. Now we know that blackbody radiation, cavity radiation, is symptomatic of electromagnetic radiation in general, which is quantized and consists of photons, and the photon energy is always E equals h nu for any frequency. But Planck restricted himself to explaining blackbody cavity radiation only. For a cavity mode of a given electromagnetic frequency nu, Planck showed that the resulting average total energy for that cavity mode was this formula: h nu over e to the h nu over kT minus 1. That was the average total energy of the cavity mode. Let's look at that graph. Now here I'm graphing it, not the average energy, but I'm dividing the average energy by kT so that so we can have one graph without having different graphs for different temperatures. The horizontal axis is h nu over kT, and so the blue curve is Planck's curve as a function of h nu over kT. The vertical axis here is average total energy over kT, 0, 1/2, 1. The curve approaches 1 for small frequencies, which means the average total energy approaches kT as we go to the upper left, which means it matches the Rayleigh-Jeans formula for low frequencies. Rayleigh-Jeans thought that the average total energy was kT for all cavity modes. Planck says, no, the average total energy is this formula as a function of frequency and temperature. and it approaches Rayleigh-Jeans for small frequencies. This is a possible time to take a break. So Planck had his formula for average total energy for a cavity mode. We can then multiply that times the number of discrete cavity modes per unit volume per frequency. Multiply them together, and that'll give Planck's formula for spectral energy density for blackbody radiation. This is the number of cavity modes per unit volume. This is the average total energy as a function of frequency and temperature. Multiply them together and we get this Planck's constant. Now that we have a version of the energy, spectral energy density, we can go back. We have the formulas to go back and produce the spectral radiance as a function of frequency and lambda. So if we substitute Planck's energy density back in, we get this Planck's law for B as a function of nu, and let's look at that graph. Here the horizontal axis is frequency, and here's the visible light range, red to violet. To the right of that is ultraviolet, to the left of that is infrared. Vertical axis is spectral radiance, the frequency version, per hertz. The green curve is 3000 Kelvin, which is hotter than the melting point of a lot of materials. It has some visible light. We can see that some of it is in the visible light range, but it has a lot of infrared. Now let's let the temperature go up to 3700 Kelvin. That's the black curve here, which is the melting point of tungsten. We see that there's more energy radiated at every frequency than the green curve. And the peak spectral radiance is higher than the green curve. And also the frequency where the peak is higher for the black curve than the green curve. Goes from here to here. The purple curve is 4000 Kelvin. The blue curve is 5000 Kelvin. The red curve is 5777 Kelvin, which is close to the light from the sun. Most of the light from the sun is reasonably well matched by considering it to be 5777 Kelvin. Now, for the red curve, still a lot of the energy is infrared to the left of this red vertical line. A lot of infrared. That's what you're feeling when you look at the sun and you're feeling the warmth of the sun. But there's also a lot of visible light, red to violet. That's what we see as sunlight. And there's also a lot of ultraviolet. Now, this would be the curve from a black body that was at this temperature. But sunlight passes through our atmosphere, and our atmosphere does absorb a lot of the ultraviolet. Not all of it, we know that. We still get sunburn, but a lot of the ultraviolet gets absorbed by the atmosphere. Now, we can also produce the wavelength version of Planck's law, and here it is, and we can look at that graph. The graph is pretty similar, but kind of flipped left to right, but not exactly. because the axis is different. This horizontal axis is wavelength in nanometers. Here's visible light. So if we go right to left, we're going from large wavelength, long wavelength, to shorter. So infrared, red, visible, violet, ultraviolet. And I'm plotting the same curves here. The 3000 Kelvin curve, it has its peak in the infrared. The black curve, the melting point of tungsten, has its peak in the infrared. But plotted this way, the violet curve, its peak is near the red boundary. The 5000 Kelvin curve, its peak is in the middle of the visible light, somewhere like light blue. And the sunlight peaks in the visible light, peaks around blue. This is a possible time to take a break. Now those two curves were spectral radiance curves. They always had, at any temperature, they always had a peak value. And we can work from the spectral radiance functions to find out where the peak is located. If we take the B sub nu formula and we try to find out where the frequency peak is, we will find that it is located here. And so that peak is linearly proportional to temperature. This is called Wien's displacement law, and it was known before Planck did his work, and Planck's results did match Wien's displacement law. We also can get the wavelength at which the B lambda spectral radiance curve peaks, and we get this formula. And at the numerator of this right side, we get a numerator divided by the absolute temperature for this peak, and that numerator is called Wien's constant, and Planck's formula did match Wien's constant. However, there are a couple things to beware. Normally when we talk about light or electromagnetic radiation, if we take a particular frequency and we want to know what wavelength corresponds to the frequency, we know that the frequency times the wavelength equals the speed of light c. But you cannot do that with these peak values because they represent different wavelengths and frequencies of light. So you can multiply the values together, but you do not get the speed of light. You get a fraction of the speed of light. Related to this, beware that at some temperature, the peak of B lambda being in the visible range does not mean that the peak of B sub nu is in the visible range, or vice versa. For sunlight, the wavelength peak is in the visible range, but the frequency peak is in the infrared. It's the same information, but those formulas are obtained differently. This is confusing, and some articles get this wrong. So if they tell you the peak is in the visible range, you really need to know, are they talking about the wavelength peak or the frequency peak? And a lot of times they won't tell you. So you need to know or think about it. This is a possible time to take a break. Now, at long wavelengths or low frequencies, Planck's formula does match the Rayleigh-Jeans formula, as it had to, because the Rayleigh-Jeans formula was accurate at long wavelengths and low frequencies. At short wavelengths, high frequencies, Planck's formula does match the Wien approximation, which I chose not to describe in this lecture. Planck knew about it though, and he knew that he had to match it, and he did. But it was add complication if I included that in this lecture. Now here's an odd thing. If Planck's constant h were not a constant of nature, but it was a variable that we could vary, which it's not, but if it were, then if we took the limit of Planck's formula as h tends to 0, we get the Rayleigh-Jeans formula. So Planck's formula would become a classical formula if Planck's constant h could approach 0. This would be like turning off quantum mechanics and having atoms behave classically. But we cannot do this. We cannot shut off quantum mechanics, and atoms do not behave classically for blackbody radiation. Now that we have the spectral radiance, we can integrate to get the Stefan-Boltzmann constant. And if we integrate it, we would find that the Stefan-Boltzmann constant is this formula, 2 pi to the 5th over 15 times Boltzmann's constant to the 4th over the speed of light squared times Planck's constant cubed in the denominator. And if we know what all these constants are and we multiply them together, we get 5.67 times 10 to the minus 8 watts per square meter Kelvin to the 4th. But at first, Planck's constant wasn't known, whereas Stefan-Boltzmann's constant was experimentally measured. So Planck was able to use that as a way of determining the value for Planck's constant. Actually, Planck used this plus another formula based on his work, so that he was able to determine both Planck's constant and Boltzmann's constant independently, and the speed of light was known. Note that Stefan-Boltzmann constant depends on h. If h could be made to be 0, the Stefan-Boltzmann constant would be infinite, and that's what the integral of the incorrect Rayleigh-Jeans equation says. But we cannot make h 0. We can't change h at all. It's a constant of nature. Physicists could get Planck's constant h experimentally by measuring spectral radiance, total radiance, peak wavelength, peak frequency. Once we have quantum mechanics, many things depend on Planck's constant, so there's many high-precision ways to measure Planck's constant, and it's one of the best measured physical constants of nature. And I will talk more about that in the next lecture. This is a possible time to take a break. Now, here's a log-log chart where we can get either total radiance or peak wavelength as a function of temperature. If you're not familiar with log-log chart, don't worry about it, but here's how it works. The bottom horizontal axis is the blackbody temperature of an object in Kelvin, and this chart goes from 1 Kelvin up to 100,000 kelvins. So if we take some temperature or some object, we'll start with this red curve. This red curve, the red line is the sun's apparent temperature as we observe it. So around 5,800 Kelvin. So we take a temperature, 5,800 Kelvin, we draw a vertical line until we hit the blue line, and then we can go left or we can go right horizontally. If we go left, we find out the total radiation emitted by the object per square meter of emitting surface. And so for the sun, we're getting something like 60 million watts per square meter emitted from the sun. So per square meter of the sun's surface. And if we follow that horizontal line to the right, we find that the peak wavelength is in the visible range. Now this chart goes from 1 Kelvin, so this vertical line is cosmic microwave background 3 Kelvin, and we see, if we want, we can find out how much power is radiated by the cosmic microwave background, and we would find that its radiation is in the microwave range. So here we have liquid nitrogen, here we have the human body, melting tungsten, some stars that are hotter than the sun. But there are higher temperatures than are shown in this chart. This chart does not go up to the core temperatures of stars, which are hotter. The temperatures of supernovae explosions, particle accelerator collisions on Earth in the laboratory, or the early temperatures of the Big Bang. This is a possible time to take a break. Planck was careful to say that his quantization of electromagnetic wave energies was only for the black body experiment. That's what his analysis was for. And the interaction between electromagnetic radiation and the atoms in the walls of the black body cavity. Planck said this was due to the quantization of the oscillations of the oscillators, which now we think of as electrons and atoms, in the cavity walls. But actually, at that time, Planck was not convinced about atoms. So he didn't call them atoms, he called them oscillators. Physicists in general weren't convinced yet about atoms in 1901, but they were getting there. Planck made no claim about electromagnetic radiation generally, but now we know that E equals h nu or E equals hf applies to all electromagnetic photons, electromagnetic radiation photons. Although Planck proposed that the emission and absorption of light in the black body cavity were quantized, he didn't fully believe it. I mean, he said it was a desperate attempt to match the experimental results. It wasn't until 1919 that he fully believed that electromagnetic radiation was truly quantized. We will have a lecture, the second one from this one, about Einstein's photoelectric effect and Einstein's proposal that electromagnetic radiation is quantized. We'll have that in 2 lectures. This is a possible time to take a break. Now, Planck's constant H is present in the equations of quantum mechanics. It's part of Schrödinger's equation. It's therefore present in all quantum mechanical results. It's present in the energy levels of electrons in atoms, and therefore the emission and absorption of light energy photons by atoms. It's present in the size of an atom. Why an atom does not collapse. It's present in the electron orbitals of an atom. You could say, well, okay, that's atoms. We can't see atoms. Why should I care? It's present in molecular bonding. The molecular orbitals, bond energy, bond length, bond angles. So chemistry. You could say, oh, well, okay, that's chemistry. I still don't care. Why should I care? It's present in how liquids and solids behave. The size of an atom determines the density of liquids and the densities of solids. And that we can observe. Iron is heavier than water. It's present in the material properties of solids. Is a solid strong? Is a solid brittle? In the electrical properties of a solid. Is it an electrical conductor, an electrical insulator? Is it a semiconductor? Is it magnetic? Is it optically transparent? Is it opaque? Is it translucent? Is it metallic, reflective? Does it have a color? So, some aspects of Planck's constant and quantum mechanics just stick with an atom and we don't see them directly in the macroscopic world, but others give rise to the macroscopic world around us. We just really never thought about it and didn't know about it. The next lecture will be entirely about how Planck's constant relates to quantum mechanics. This is the end of lecture A3.